Well, yes. Okay, so we're starting the review. It's still very hard to see the smartboard because the lighting is just really low. So I'm going to use the side whiteboards. Just type a question if you have anything, and it'll pop up. Okay, so what's up?
Can we do
From the homeworks or?
it's from the homework. It was on the last section.
Okay. Okay. What's the problem? Straight as well?
Yeah.
Homeworks? Which one? Rotating triangle?
Yeah.
Okay. So start from the beginning, or do you have a specific?
No, I just like trying to understand.
Okay. So let's just do. So we're gonna do. Nobody by chance has the next one. So we're doing unit 17 Faraday's law, which is the rotating triangle in the constant field field. So let's just start from the beginning, and then we'll just go through. Okay, so they asked, so you're given a few things, right? And so you have a triangle, B field coming out of the page, right? B field on the page. Here's a triangle, and you know this is the y-axis here. The x-axis here, so that's not, you don't have to worry about that. And you know it's rotating this way. So meaning it's coming out of this half, coming out of the page and going this way. Okay? It's rotating like this. Yes. Right?
Mm-hmm.
Okay, so first they ask you what is the angular frequency of rotation? So the angular frequency is given by omega. Right? And you have a few equations to find it. You have a period and you have 2 pi. Right? And so you know that you can use, you're given a period of, well, everybody's will change, but it says that one complete rotation in time t. T can be whatever number you have. You know that one complete rotation equals 1 period, which is t, which is signified by capital T. Now, does everybody know what one full period is? I mean, or is that confusing? Because I can explain that. One period is one rotation per per unit length of time. So if it says one rotation per second, meaning every second it goes from. So every second it goes from this position around and then back to this position. That's one rotation. Okay, so you're given t, and you know the formula is omega is 2 pi over t. Okay, it's 2 pi over t, and you know the units, and you can always check your work because the units for omega is frequency, right? It's a form of frequency which is hertz. So 1 over second equals frequency. frequency is, it's a unit, it's it's a blank, it's just units on the top per second. Okay, and it's called hertz. Which is signified by HZ. Okay, so you use that, you plug it in, and then you get whatever number hertz. That's frequency. So now number 2 is they ask you what is the magnitude, the maximum current induced in the loop. Okay. So you have an equation which you can find given, right? So you can do some algebra and you get the equation number 2, 1, 2 of phi, right, is equal to B, magnetic field, 1/2 BH, base times height, BH, cosine omega t. Omega t, where omega is what you found here, and t is at any given time. Okay? Because it oscillates. That's why it's a function of cosine. Right? Solve that for we can use this equation, get I max equal to did I ever sign it?
Oh, 6, 9, 7 people. Something's up.
Where's okay. Use that for 2. And then for T, or for for letter C, they just give you a certain time. So at time, I have 0.525 seconds. Okay, but now you have to realize that it takes, well, everyone's different numbers will be different, but it takes 1.4 seconds for me to make a full rotation. Okay, so that means half, when this triangle will now be drawn like this. To get the triangle into this position, right, will be period divided by half, correct? Or, yeah, half. Because it goes, huh?
Let's have it coming out.
Like this. Okay, so it rotates like this, right? So when this point, view everything in regards to this tip. That'll make it easier when you're trying to figure out what position it's at. It'll go through 4 quadrants, right? This will come out like this, so it'll be straight. This point will come here, so it'll be like this. This point will be in the back, so the triangle will be in the back, and then it comes back. So 4 different main positions where it will be, right? So when it goes from here to here, you have half. And it goes out and over. So now it's halfway through its rotation. So you take your period, right, which is how much time it takes to get through one full rotation, and you divide that by 2. So you get whatever number, right? And then they ask you for the third part, it's what's the magnetic flux given at time t equals whatever, right? So then you know that, let's say, I think I have 1.4 seconds. Yeah, I have 1.4 seconds. Equals 2. So for me, t equals 1.4 seconds. So if I divide that by half, I know I have 0.7 seconds for one rotation, right? What's up? So 0.7 seconds, this is here, correct? And they're asking at 0.525, right? What's the current? Right, that's what they're asking, current for the third one?
Magnitude flux.
Oh, they're asking for the flux, yeah. Okay, so at 0.525, if I take 1.4 divided by 4, I will find whatever it's over here. Can someone do that just to make sure I'm not doing this? What's 1.4 divided by 4?
0.35.
0.35? Okay, so at 0.35 I'm here. So if I get 0.5, I'm between 0.35 and 0.7, right? So I think it's about what, halfway, 0.35. Do 0.7 plus 0.325 divided by 0.535 divided by 2, should be 5.525. No, that's like 4.
0.525.
Yeah, so you're about like this, anyway, right? So you're about 45 degrees off from here, from this position. So they ask you for the flux. You know that the flux is given by the equation like this, the same equation here. This is the equation of flux, right? Correct?
Yeah.
So you use that same equation, and then you plug in your time 1. Correct?
So all you're changing is the same thing, you're just changing the time.
Right. But you know that, like I said, at 0.525 or whatever numbers you guys will have, you'll be 45 degrees from either this half or that half, right? So cosine of 45 is 1 over square root 2. Or no, it's 2 over square root 2. 2 over root 2, right? And well, yes, omega here will come up to be that, yeah. So you plug in your time to find out what your cosine angle will be, right? You plug in whatever time you're given, and then you just plug in that into this equation here. So in the end, what you should end up with is something like this, where your flux is equal to b 1/2, same thing as this, b times base times height, right? But then it'll be 1 over square root 2, because you're at a 45 degree. And I'm pretty sure if I work out this might come up, this will come up. I didn't plug in my numbers. Whatever this comes out to, we'll make it nice. Okay, but the main thing to remember is where is the triangle, right? What orientation is the triangle at the time you're given? That's something to remember.
For the first part of it, it's
Remember,
the angle
uh-huh.
is omega times the period.
Over here?
Yeah. The under cosine, yeah.
What is this one?
It's omega times the time that you get enough period. She's asking if that t was the period. It's just that it'll give you a
this is the time
time.
that you're given.
It'll tell you what time, what's the flux at this time, and that's what you plug.
T, the big T is period. And little t is time in seconds at any given moment. Yeah, they're two different. In physics, you'll use the same variable a lot for different things. Just keep track of that, especially R. You're going to use R for like, literally everything. It's really stupid, but it's all right. Okay. Doing me keep going through it? Do you think we can go into it? Yeah? Next questions? Any other questions for homework? Or?
Yeah. I'll just go ahead and give it to you.
Is it from the sample again?
Yeah, it's number 7.
Is this labs? No, I'm thinking. Okay. Is the light blow? Light did blow up, didn't it?
Yeah.
Okay, we're writing on this one. Okay, we're writing on this one because the light blew up. Okay, so you have the slide, you have the two, this is number 7 from practice F13, call 13. So we have 2 infinite sheets of current. Here. Okay, I'm going to draw it on this, and then I'll do the word on here, okay? So let me know if you have problems seeing this. Coming out of the page. Oh, sorry, this is going in, this is coming out. And we're doing, okay. These 2 distances are the same, x naught. Okay. You have some point out here of r, some point here of p, and some point here of s. Okay. So for the first one, can everybody see the red properly? Okay, so we'll do any magnetic fields given by this slab red. Okay, and how about the green? That's differentiable from the black, right? I don't know, I can't see it. Is it differentiable from the black? Yes? Okay. And any magnetic fields given by this sheet will be in green. The first question asks, draw the magnetic fields given, draw the net magnetic fields. Okay? So for this one, you have to use the right hand. Remember, magnetic fields are infinite. Okay? They can cross over and overlap with other magnetic fields, but they are infinite. So the magnetic field from this sheet will also reach everything on this half, and the magnetic field from this sheet will also reach everything on this half. Okay, so just remember that. So now this is going into the board, right, because of the x. So the magnetic field here will be going down. So this is draw like this. And here will be going up. Okay? And same thing on this side, because it's on the same side, the magnetic field of S will also be going down. Now we'll do the magnetic field for here. This is coming out of the board, so over here, it will be going up. And because the right half is going up, you know, everything automatically on the left half will be going down, right? So we're going down, it's also going down. Now he has to draw the net magnetic flux. So you have to take into account the charge density and the charges on the wire itself. Okay, so there you give that. So your N your charge density is 25 wires per centimeter. Okay. And the current I2 is double the current I1. So this is I2, this is I1. And this is number 2. Okay, and that's twice the current of this. Now the wire density on both of these are the same. Okay, meaning the net total current for 2 will be greater than 1 because the wire densities remain the same. Okay, if you have different wire densities, that would be a different case. But because the wire density is the same, you know the total net current for this one will be greater than number 1. Okay, so now that you know that, you know that given at this position, now I'm going to do everything in blue. So okay, now you know that everything closer to this point, or closer to this slab at point S, will have twice the greater net force going up than it is going down, correct? Everything here. Because 1, it's closer to charge slab number 2, and 2, because this sheet has twice more current. Yes, so net charge will be going up. Okay, now you look at it for this one. Here, both of these are going down. So you don't have to worry about finding out which one will be higher or lower. Here, both of these go down. Okay, now this is the one you have to think about. Here, you have to think about, okay, this is really far, but it doesn't matter because the magnetic field from these sheets will be infinite and at the same magnitude essentially at all the points, right? So again, you have 1 going up, but you have 2 going down. So your magnetic net will be going down like this, right? Yeah, because this is going into the board, and that one's coming out of the board. Okay. So now saying, how do the magnetic fields, how do the magnitudes of the magnetic fields compare in these regions? Okay. So what equations do you guys have for the magnetic fields from infinite sheets? Give me equations that you think could be applied to this type of situation. Huh? Yeah. Okay. So you have B and 1/2 mu naught and I. Where mu naught is a constant, N is the charge density, and I is the current given. Right, so this is that. So for 1, so you have, let's do 1. Okay, here what you can do is you can cancel out the mu naught, right? Or you can cancel out the mu naught and N because they're both the same. Right? Mu naught is just a constant, right?
Yeah.
Okay, and you know N will be the same for both because it's given, but the charge density for across, it didn't say specifically for 1 or 2. So if they don't say specifically for 1 or 2, you can just assume that it's the same. This goes away, this goes away, and you know that I2 is equal to twice I1. I1. Okay?
I think he just wants you to find the equations.
Yeah, so here he says in each of the regions, find the magnitudes of the net magnetic forces in the region,
Oh, it means at each point.
in each region, or I guess in each point, because each point is in one region, right? So here you have one region, because it's on this side, meaning like, yeah, both are acting on it, but see how it's like separated, right, between these two and here. Let's call that one, call that two, and call that three. Okay, regions 1, 2, and 3. So for region 1, so let's make region 2, because we know region 2 will be the easiest one, right? You have both of these being added, correct? So you'll have this one added to this one, right? And it's in the negative direction because it's going down. Yes? Okay. So, let's just put that on the bottom. You won't be able to see it. Let's put it on the top. I1. Oh no, P3 is 1/2. Okay, for region, oh, sorry, this is region 2. What am I saying? Region 2, this region. Sorry, that's my mistake. That's region 1, 2, and 3. I'm calculating for region 2. Region 2 is the easiest one to calculate because both are going down, right? Both the red from this and the green from this are going down, so you just have to add them. Yeah? And because both are going down, they'll both be negatives. So this 1/2 will be negative, and this will also be negative.
Mhm.
This?
And you're adding them together?
Yes.
Then why is there only one I?
Oh, I1 is the current from 1 because I2 is 2 times I1 right here. So you replace that, so now you're left with only one variable of current. You don't have to worry about what current 2 is. Everything is in form of current 1. So when you add them, they all add up easily. Right? So, yes? No?
Yeah, I got something different if you check my sheet.
Okay, so your thing is correct where the net force is down. That's right. So now let me just write it over here. Okay. Region 1, 2, and 3, right? Yes. Okay. He asked to find the net magnetic field in each of the regions. So now you know that here the two are in opposite, so you'll have to subtract them, one subtracted from the other. Here, same thing, they're in opposite, so one subtracted from the other. Here, they're the same direction. So you know this will be easier to calculate because they're in the same direction, so you just have to add them up. Okay? So for B, B given from slab 1 is 1/2 mu naught and I1, correct, from slab 1. And the B given from slab 2 is 1/2 mu naught and I2, correct? But you were told that I2 is 2 times I1, right? So you make a substitution and you get B from, let's just say slab 1, or sheet 1, right, to not confuse with region 1, is equal to 1/2 mu naught n I1, n is the same for both, and the B from sheet 2 is equal to 1/2 mu naught 2 I1. Right? You just made that substitution because this essentially is I2. Right? And now both are pointing in the negative direction. Right? Because with respect to your x and y axis, both magnetic field forces and fields are pointing down. So it'd be negative. Right? So it'd be negative and negative. So because they're both pointing down, well, mostly because both are pointing in the same direction, you just add them up. Correct? So if you add these up, you can factor everything out and just add the coefficients up, right? And you get negative 3/2 mu naught n I1. And this is B from region 2. Yes. Right, that makes sense?
Yeah.
Okay. So you can follow a similar process, right? And get B for region 1 and B for region 3. So if you guys want to do that right now on your own, you can do that, or I can do it for you, but I think like given it's only 20 minutes left, we can move on to other stuff. But I'll go through it if you want, it doesn't matter.
The thing I was stuck on was the next question, actually.
The next question. Okay, let's do the next question.
About trapezoid.
Okay, so the next question says, so you have a trapezoid like this, right? Let's get rid of all this stuff. See. Okay, and you're told that this is H. Okay, from height from A, B, C, D. Okay. Okay, so given the I1, given H is whatever it is, and I1 is 0.55 amps, just remember to convert the centimeters to meters. Keep everything in standard units, meters, amps, stuff like that. So it'll make everything easier. What is the integral of B dot dl around the trapezoid? Here you go. Yeah, can I get rid of this side? Yeah, even the bottom stuff. Yeah. Okay. Okay, so you have the integral around the closed loop, that's the school circle means closed loop, B dot dl. Okay. Now, you know what the B field, the equation for B field is mu naught I inside, right? That times n. Okay. So it's mu naught I inside, which is whatever current inside that loop that you're trying to find, times your wire density, right? Times the height, because the current affects this whole height, correct? Times the height. So this part comes from the B, and this from the DL. Right, because B is constant, so that gets pulled out of the integral. DL is just L, which is length or whatever distance you have, and that gives it this height. Okay, so this is your equation: mu naught I inside n times h. Okay, so we plug in mu naught. We have our I inside of 0.55 amps. We have N of 25 wires per centimeter, so you have to convert that into wires per meter. Or what is it? Yeah, wires per centimeter. Convert that to wires per meter. You get 2,000 per meter times H, which is what, 0.053 meters? Okay. So here, the meters cancel out. What's the units for mu naught? So once you write out mu naught and you write out the units, you'll see that some stuff also cancels out, and then you're left with your answer. Okay. Other questions? Checkpoint? Which one?
Chapter 16. The last one.
Motion EMF?
Oh, yeah.
Induced current as a function of time. Okay, let's write this up. Oh, making good progress. Can I delete this? Goes on. Can I delete this? Yeah, first. Okay, so a loop. This is your B field coming out of the screen. And you have a loop on the right hand side with the velocity going that way. Yeah? So the equation you can use is F equals V L cross B, right? That's whenever you come across a problem and they give you values, right? Like, okay, you have a velocity, you know the B field, it's a loop moving through a B field. Some equations start coming through your head, you should write them down to see what equation you might be able to fit in here. Right, so the first thing that comes to my mind is F equals V L cross B. V is velocity, V is the B field, L is the length of whatever wire segment is inside the B field at the time, or at the edges of the B field at the time. Okay? So now they ask which plot best represents an induced current in the loop as it travels from the left of the region to the right and then completely out. Okay. So remember now, when something travels inside the loop, okay, I'm going to use different colors to represent 3 different periods of There are 5 different periods of time. I'm going to use different colors to try to represent them. The first one is here. Okay. The second one will be like this. I'll just do it. The third one will be like this. The fourth one will be like this. And the fifth one will be like this. Okay, all are moving to the right. So now you know that an induced current will happen at the edges of the, when it's inside the field, right? On this, so at 1, no part of the wire, at phase 1, no part of the loop is inside, okay? So for that point, can I get rid of this, guys? This. So at phase 1, you know that an induced current will only occur when you have a part of the loop at edges of your B field, right? So at phase 1, you'll have nothing. And here, let's go to phase 1. Where's the blue marker? So at phase 1, you'll have nothing, right? Because it's nothing in there. Now in phase 2, once the first part of the wire enters, and as it travels through, there will be an increase in current. Correct? Because all of a sudden, across this boundary, the charges will split. Correct? And the charge will continue to split as it moves across, all the way to the end wire. Okay? So you'll have a spike. And as the loop moves through, the current will be the same because your L is the same. Correct? So it'll go across. And now at phase 3, so this is phase 2 here. 1, 2. Now at phase 3, the whole wire is inside. Now, let me re-say that. Once it passes 2, the current will drop, correct? Because now no part of the loop is at the edges of B field. So the current will drop. Okay? Now for this distance, the loop is still traveling inside the B field. So it will continue to go. And now this is part 3. Now at part 4, it starts to come up, correct? But you have to remember that when it comes out, the force induced at this side will be different than the force here, because the force will always try to push it forward, right? There's going to be an induced current that will try to stop it from going, right? That's what we learned. Remember in class you did the thing where you drop something and then the induced current may go really, really slow through the pipe. You remember that? It's the same logic. It's going to try to, the induced current will try to make it go as slow as possible. But once it gets to this point, the induced current goes in the opposite direction because it's now exiting the B field. Correct? So it will go in the opposite direction. And the same thing where while the whole loop exits, the current will stay the same, again, in the opposite direction. I'll try to push it out, right? Try to just get rid of it. And then it goes back to where the last wire is, and then it cuts off, because now the whole loop is left the B field. Like that. So that's the graph that's given here. A lot of people might have got confused with B, but remember that the induced current will change depending on which position it's at, either the front or the end of the loop, if it's entering or exiting. Okay? Okay, we have like 5 minutes, so any other questions or anything like that? I know he gives you guys an equation sheet, so I won't give you mine because, let's be honest, it's a lot. But if you want to take a picture of mine, just to know that which equations fall into which category, because mine is like extremely categorized. It's like Faraday's law, induction in RL circuits, motional EMF. It's extremely categorized, like for generators and non-uniform B loops or whatever. You can take a picture of this if you want. If not, wish you the best of luck tomorrow and on the rest of your finals. And there's also no session tomorrow night. I sent out that email along with this one. There's no session tomorrow night because I won't be on campus. I have to go somewhere. Okay, sweet.
Can you take a picture of your sheet?
Yeah. Can I have my paper back?
So what's the unit for integral beta DL? STM?
Yeah, I think it's what,
What, like-
Tesla meters, I think.
And the hormone just blocks STM square.
Well, I think that's because you have the dot DL. I think flux is just what, integral of, oh, you got DL. Oh, it's B dot DA, that's why. What we used here was B dot DL, so it's just 1 meter. B is Tesla, right? And L is length of meters. Flux is B dot DA.
Oh,
So
flux
area.
is, oh, yeah.
So it'd be meters squared.
Can I take a picture?
Yeah.
It's just the front page that's in this exam,
So
right?
flux is
My exam covered everything, so I don't know. Like, you can,
square and then the integral beta DL.
Yeah.
my exam covered all that stuff.
Can you guys share your knowledge?
All right, good luck.
Okay, so for rotating loop,
Mhm.
okay, so for the rotating loop, flux is this, and then the integral of this is this. It's not integral of the derivative of this is EMF,
Right.
right? And that's for the one we did for homework.
Mhm.
But then, what do I use this formula?
It's for a generator.
How do I know this generator?
The generator looks like this. This is one of the things we did in class. I think this was one of your whiteboard problems. Generator looks like this.
비행기 종류는 하나 아, 있을 것 같긴 한데. 지금 사도 쓸걸? 야, 내 주변에 그런 바이오에서 카드.
A generator, it'll say generator. Generator will like specifically generate. I think it should say generator. But I don't think it's gonna work.
나오가 있었는데.
A rotating loop can just be a loop rotating inside like a field like this. Right? Yeah, something like that. I remember we had this. Right? That's also a rotating loop. The generator generally has this format because your loop will have something that looks like this. Where these are the two prongs, and this gets connected to a motor or an alternator or something like that. And this then puts out energy. So generally, you'll have these two prongs at the end to symbolize that this will, while this rotates, that gets put in like an energizer or something like that, and that creates energy. Rotating loop is just something like that. But anything that has like this type of setup, where you see this big block thing, that's your generator.
Thank you.
Yeah, good luck.
Thank you.
See you guys next week.
Bye.
Bye.
I need some
Okay, so that